This is Dr. Holt. This is AP Physics C. In this video, I have a basketball. It's going to roll without slipping down an incline. We're going to give the angle of the incline as theta. We're going to set the static coefficient as mu of s. We want to model the ball as a thin spherical shell. In doing this, we want to find the acceleration of the center of mass of the ball. We want to find the frictional force acting on the ball, and then we want to find the maximum angle of the incline for which a ball will roll without slipping. And again, we're going to do these in terms of variables. First thing I would do, we'll draw kind of a picture of what's taking place here. So I'll come up here, I will draw a line representing the incline here, like this. I'll make this just a little steeper. I'll move this down actually. Let's move this down just a little bit so I have some space. Okay, I'll draw a basketball up here. Bring that down here. We will make this angle here become theta. Alright. Now I'm going to take the basketball. We're going to draw a free body diagram, what's taking place at this. I'll make the basketball a little bit larger. I'll draw a line to represent that slope, maybe off a little bit with the angle, but I think you'll understand what I'm saying. I'll de-emphasize the line so you can see that. Alright, if we draw our free body diagram of the basketball, we will have the force of gravity coming straight down to here. So we'll have this as the force of gravity, and we'll set that equal to mass times gravity. I will have my normal force going back up, which is perpendicular to this surface here. Like that. And that'll be my normal force. And then since the ball is rotating in a clockwise fashion here, my frictional force must be creating a torque to make it go back up this way. We'll call this our F of S. Alright, now I'm going to tilt my axis a little bit. This is traditionally how I do this. I'm going to grab all this. I will clone that. Whoops, sorry about that. I'll do that again. Well, that doesn't work very well. Let me grab it. Let's edit, copy it. Come down here. Paste that in position. Bring it in here. Okay. Now all I'm going to do is I'm going to create a new axis system here. I'm going to extend this on out. I'm going to make this my x-axis. And you can see my normal isn't quite perpendicular. I'll make it look more perpendicular than what it is. This will be my vertical axis. Going up about like that. And again, I'm going in probably a lot more detail than I would if I was personally doing this problem, but I want you to understand where everything's coming from. I will make this my y-axis up here. And again, I'm just going to color this red. Alright. I'm going to take this and break it into the two components, one perpendicular and one parallel. So there's one perpendicular and there's the one parallel. Now, if this angle here is theta, this angle here will also be theta. And you can prove that with geometry. I'm not going to do it in this video. But if you want to prove that, all you have to do is come up here, quickly talk about this, draw yourself a line that's perpendicular here, and then draw yourself a perpendicular line to the surface, and you can find out very quickly if this is theta, this angle here is theta, because this angle here would be 90 minus theta, and this angle is 90, so that has to be theta there. But again, if you want to prove it, just do it on your own. You can do it very quickly. Alright, I'm going to call this here is going to be mass times gravity times the sine of theta. And this one here is going to be mass times gravity times the cosine of theta. Alright, I'm going to go ahead and remove this one in from my picture. I'm going to move this one back in to grab him. I'm going to move him back in to where he would be. And as you can see, move this up here. Oops, all that matter. Sometimes it doesn't work. I'll just rewrite it. mg sine theta. And I'm going to erase this. Alright, so here we go. The only other thing I'm going to have, and I like to do this in my free body diagram, is draw the mass times acceleration here. So I have mass times acceleration. Alright, so now all I have to do to try to solve this problem first is to say the summation of forces in the x direction must equal to mass times acceleration. Alright, I'll let anything that goes down be negative in this case. Again, you make it positive, it makes no difference whatsoever. When I do that, I will get F of S, my static friction, which we will let to be positive. I'm going to drop my vector over the top of this for right now, minus mg times the sine of theta is equal to minus m times a. And again, be very cautious about the signs here. Alright, at this point, let's talk about torque, because this static friction is creating a torque that's causing this basketball to rotate in this position there. Alright, we know in the study of torque, we know that torque is equal to the moment inertia times alpha, or the angular acceleration. We also know that if the basketball has acceleration, I can model it basically around this point right here, because this point is touching. Then I can make that my angular acceleration, and we can say, can we not, that acceleration of the center of mass must equal to alpha times the radius of the basketball. If I take this again, this is my angular acceleration. If I multiply that by the radius, I will get my acceleration for the center of mass. Alright, so we'll go back to the torque equation. What is our torque? I'm going to do it this way. Anything that goes this way, I'm going to make negative. Will I not have on this side of the equation, I'm going to have my static friction times the radius of the basketball. We'll make that negative because it's creating a clockwise torque, is equal to the moment inertia. Now a basketball, they said to model that is a thin spherical shell. If we do that, then if we go to equations for inertia for thin spherical, we're going to get 2/3 mr squared. So I will put 2/3 mass of the basketball times r squared. And I'll go ahead and put alpha in here for right now. Alright, we also know, as stated above, that alpha is equal to the acceleration of the center of mass divided by the radius. Alright, now one thing I made a mistake here. Make sure you put a negative there, because again, we're showing angular acceleration to go this way, so it's also going to be negative because it's going clockwise. Alright, so now let's go ahead and put this in as minus static friction times r is equal to minus 2/3 mass times radius squared times acceleration of center of mass over r. We will cancel what we can. R is gone here. That's gone here. Now I have an r here, we can cancel that out right there. So now we're down to the equation of drop the negatives, that static friction is equal to negative 2/3 mass times the center, times the acceleration of the center of mass. Alright, so now we go back and we'll start plugging things in as we go along. We go back to this equation right here. Let's see if I can grab that, not grab anything else maybe. We'll copy that. We will bring this down to this. Post that in here. Okay, I'm going to take out the static friction. Now, I don't know why I didn't drop the negative. Sorry about that. I'm going to get rid of the negative here. Because again, I had a negative on both sides. I apologize about that. Okay, so there's my value right here. I'm going to take him right there. I'm going to plug it right back into the equation right here. When I do that, I'm going to get 2/3 mass times acceleration of center mass minus mg times the sine of theta over to negative mass acceleration. Now this acceleration is also going to be the acceleration of center mass. I will move this over to the other side and get our A's together. Acceleration of center mass. I'll rewrite that again, sorry. Move this over the other side here. I'm going to get minus mg sine of theta is equal to minus m acceleration of center of mass minus 2/3 mass center mass. Okay, I'll cancel out my m's here, here. I'll cancel out my negatives here, here, and here. I will add this side over here together, and I'm going to get g times the sine of theta. So I got m times acceleration center mass plus 2/3. That's going to give me 5/3. So 5/3 the acceleration of center of mass. Move the 5/3 the other side, so we'll multiply by the inverse, and we will get 3/5 times g times the sine of theta is equal to the acceleration of my center of mass. Okay, so we'll go back to our problem, our question anyway. The question here was to find the acceleration of center mass. Again, that's going to be 3/5 g sine theta is equal to the acceleration of center of mass. All right, so we got A done. Now it says find the frictional force on the ball. I will go back to this equation right here. I'm going to see if I can grab him and not grab anything else. Okay, the only thing I'm going to do different here is I'm going to take out the acceleration. I'm going to put in what I found out here of 3/5 g sine theta. I will move this to the other side. We will solve for static friction. Static friction is going to equal to minus 3/5 mg sine theta plus mg sine theta, and I will get static friction is equal to 2/5 mg sine theta. All right, I'll go back and fill that in, 2/5 mg sine theta. All right, C says find the maximum angle of the incline for which the ball will roll without slipping. So what you want to do in these type of situations when you have a ball that's rolling without slipping, what's going to take place in this case is the acceleration of the center of mass must equal to the angular acceleration times r. If that's not the case, then what's going to happen is the basketball is going to slide. So I will take the static friction I solved here, and I will set it equal to the largest static friction I could have, which is going to be the normal force times mu. So go back down to here. Now we know the normal force is going to equal to mass times gravity times the cosine of theta. That's my normal. Again, I'll go back and tell you where that's coming from. When we broke this into our free body diagram, this normal force here, should label that normal force, that's equal to mg cosine theta. So I take mg cosine theta, I will multiply that by mu of s, I will set that equal to 2/5 mg sine theta, and now solve for theta. I will cancel out what I can. My mass has gone here and here, g has gone here and here. I will divide by the cosine of theta and bring the 5/2 over. When I do that, I will get 5/2 mu of s is equal to, now the sine of theta over cosine theta is tangent of theta. I will solve for theta, and when I do, theta is going to equal to the inverse tan of 5/2 of mu of s. I'll go back and fill that in, inverse tan here. Of 5/2 of mu of s. And that would equal to the maximum angle. Just make sure I did not make a mistake there. The 5/2, isn't it? Yes, 5/2. Alright, so that's how you that's how you solve this problem. That's part A, part B, and part C. Alright, very tedious problem. I hope this video was useful. Best of luck.